So what a pleasure to be here in Kyoto after 4 years of preparation. It is my pleasure to be here representing the team that wrote Chapter 2, and that was Catherine Zucker from Space Telescope Institute, Alyssa Goodman from Harvard, Stefan Meingast from the University of Vienna, and Phillip Galli from Sao Paulo. So let's start with the very obvious. This is the entire sky as seen by Planck. In blue, you have the local interstellar medium. Now, we care a lot about the interstellar medium because this is what fuels star formation and galaxy evolution and planet formation. We care specifically about the local ISM because it's the only place in the universe where you have the resolution and sensitivity to solve the star formation puzzle. How do clouds collapse, how do clouds form, and these are the cards we are dealt. Now, we could do a couple of things. We could do what Mark said, just it's too complex. It is a beautiful mass. Let's just take all the pixels and study them statistically. What I'm going to argue today is that's probably not the best approach. What I'll talk to you about is the results from the Gaia mission. Gaia, a satellite that is measuring the proper motions and the distances, a parallaxes to more than 1 billion stars. A satellite that was not designed to study the ISM or star formation, I will argue, is opening fantastic new avenues and insights into the field, our field. Here's a brief outline. I will talk a bit the pre-Gaia view on a local Milky Way. I will have to talk about the Gould's belt, the model of the distribution of gas around the sun and star formation. And then I'll talk about the 3D dust maps, perhaps the most recognizable product you know from Gaia. It is this 3D dust maps. And talk about this first tests and first results we're doing into trying to measure the 3D motion of the ISM. And then I'll talk about young stars, and our young stars, not the ones that we learned about from missions like Spitzer, from 0 to a few million years, but from a few million years to 100 million years. So it was a fantastic missing gap that Gaia is closing. And I'll try to put it all together in the end. Now, there's a lot of 3D interactive pictures. Gaia data is 3D data. From my experience, it always pays off to spend some time in looking at the data in 3D. Now, we all do need to publish in 2D for papers. At the end of this, if you have the PDF, there's all the links to the interactive figures. The chapter has interactive figures. You should try to play with them because it is a new world. So here's the pre-Gaia view on molecular clouds. First, we learned about molecular clouds from early 1900s, the advent of photography. These obscuring masses, are they real or are they not? Yes, and then came the star counts. We know how to study the structure of these clouds. And this is from continued observations. This one is from Herschel, a beautiful high-resolution, high-dynamic range map of the Perseus clouds. Perseus is about 200, 300 parsecs away. 1970 discovered the advent of molecular spectroscopy. We got one extra dimension. We now know about the dynamics of molecular clouds. In fact, most of what we know about molecular clouds come from observational molecules such as CO, CN, and ammonia. Now, this was not the other side of Perseus that I just showed you. This is just you rotating a cube, a PPV cube. And the promise that if you had told me 5 years ago that we will be talking about really PP view of Perseus, the true other side, other side of Perseus, I would not have believed it, but I'm going to show it to you today. So, how is this gas organized around the sun? Well, this is a model that goes 150 years old. This is Benjamin Gould. He was fascinated by massive bright stars for him that were, making this band about 20 degrees off the plane of the Milky Way. This is actually were found by John Herschel, and it basically was Cosine and Orion stars. They were fascinating for him. Over the 60s, 70s, we learned that stars, massive stars, or bright stars are massive stars are young stars come with dust, and by the 70s, we had a pretty good idea that there was this ring around the sun this Gould belt ring made of young stars and dust and gas. And this has been a very successful model, and it was crystallized by the results of Hipparchus, the mission previous to Gaia, where the observation of young associations, OB associations, showed some sort of a ring, and also seen here in the same data, but these are just OB stars. This is all, again, Hipparchus. You could see it from X, Y, and then, by the way, all the plots on this talk X, Y Cartesian point galactic center to the right, direction of rotation north, and of course Z to the galactic poles. So you could see some sort of a ring already in Hipparchus. If you see from the side, there's your 20-degree inclination, and this is from the other side. Now, while this was well established, there were some discord, some voices against or not seeing this. This is work by Hervé Bouy, where he does a reanalysis of the Hipparchus data with kernel densities, and it's really not a great ring, more than it is some sort of elongated structures of OB stars that he calls blue streams. Now, the first recognized product of this Gaia mission in terms of ISM is 3D dust maps. So we knew about 2D dust maps. We were doing star counts in the optical a long time ago. With the advent of large surveys like 2MASS in the infrared, we can actually use the background stars to a molecular cloud and use, not in a statistical way, but use their colors to construct very accurate maps of the distribution of gas inside a cloud. So what does Gaia bring? Well, Gaia brings the distance to all the stars, the ones that are in front, the ones that are in the back. And what you have then is this beautiful case of you know X, Y, Z points, and you're trying to reconstruct a medium that is traced by these X, Y, Z points, the classical inversion technique problem. And several people have been working, several groups have been working on them and making absolutely stunning maps like this one. So these are the first 3D dust maps of the ISM on kiloparsec scales, sun in the center. What you see on all this, the differences are mostly Gaia data version, the data, and the techniques used, but overall you can see they're tracing the same thing. The surprising part here is there's no clear, we say there must be a local arm and the spiral, Sagittarius arm and the Perseus arm, and they're not really clear. Another surprising thing, where's the Gould's belt? Maybe there, maybe that's the Gould's belt. So we were interested in this topic, and we decided to, instead of using all the data to reconstruct to the 3D maps, you can gain a bit in the quality of your measurement, the distance, if you ignore everything and do something even more basic, which is a version of the Wolf's diagram. Just take a direction towards the cloud, this Orion A, and just take all the stars along this aperture and plot them on a diagram of extinction versus distance. And what happens is, there's essentially no extinction near the observer. As you go further and further away, there's no extinction until you hit the first wall of extinction to your cloud. That gives you a better handle on the when do you encounter the wall of dust to your cloud. And this was before Gaia, and the game was all about, so here are your stars, and gray meaning are the uncertainties, and the game was about exactly where do I do the line, where do I touch the cloud, and there was this basically uncertainty. If you use, this is before Gaia, if you use Gaia data, this happens. So your errors become very, very small, and you can then make very accurate distance to your cloud uncertainties before Gaia and after Gaia. Now you're now seeing, well, really? Can you really trust the dust? Because you're just touching a surface. And this was something that very serious people point to me as, well, this is a problem with the technique. It is not a problem because the errors that we're talking about here are essentially the size of your cloud. So we're perfectly fine with this. And best, we can compare with the golden benchmark for distances with our masers. We can measure distances towards towards these masers using dust, and you see a one-to-one line, 10% scatter, no obvious deviations from it. So the big advantage then is that there's about 200, 300 masers, and there's infinite lines of sight here. So suddenly you don't have only 200 distances, you have how many distances you want, as long as you have stars and dust. So with this, let's now figure out exactly where's this Gould's belt. Here's Gould's belt, the clouds we all love and adore because we spend our lives studying them. These are the ones that have, you know, the young stars that most of us are studying, the disks, the young disks that some of you are studying, and the planets forming, and supposedly this is the Gould's belt. Immediately you notice, hey, what's wrong with this? Why are not they in the Gould's belt? So we take them all, we took all the measurements we could. Once you have all these measurements, you have L and B, or a direction, and you have a distance that you can convert to Cartesian coordinates. And when you do that, this happens. So now we look, I'm showing you the bird's eye view down on the Milky Way. Here's the sun, and this is where all the molecular clouds that I was showing before. I have to show you again because it's hard to see. This distribution, this beautiful mass, turns out to be organized in two single families. So this very narrow, a very long, straight structure that we call a Radcliffe wave, and the split, this is the Rosine-Lallemand work. So we called it the Radcliffe wave because it's a wave. When you look from this side, it undulates around the galactic plane. Why? We have too many ideas. We have no clue exactly which one is the right one. This is work in progress. Is it oscillating? Ask me about that in the end. And here's a view from the end on. Now, 3 kiloparsecs, we just heard about how the molecular clouds form. And here, I think you have the best laboratory that you can imagine for cloud formation. You formed a structure that is currently forming stars at both edges everywhere. There's no way information traveled from this part to even the next one, to the next star-forming regions. The star-forming regions, the GMCs, are separated periodically along this structure, just like face-on galaxies. Then you start to realize, wait, maybe this is what these dust lanes on face-on galaxies, which was very hard. We had a hard time convincing ourselves because it's so absolutely straight and narrow. But this, I think, holds the keys to understanding cloud formation and GMC formation. This is the mother of the GMCs. All the star-forming regions that lie within them, none lie outside them. How do you build this thing? Not with feedback. Feedback will act of 500 parsec scales. This is at least 3 kiloparsecs. This must have been the galaxy. And do you see this in other galaxies? Before I leave, here's the names you need to start memorizing. There's no Gould's belt. Ask me about that in the end if you want more proof. There's the Radcliffe wave. There's the split. There's the Sagittarius spur. There used to be, we thought, you know, the canonical Sagittarius arm that everybody was sure was there. It's gone. There's an orthogonal feature. It's not gone, but it's much more complex. There's the Sagittarius spur. This is Mike Kuhn's work. There's another spur there, the Cepheus spur. This is Pantaleone Gonzalez. And these 4 structures are the ones that are now our neighbors, and this is where most of the local star formation is taking place. So do we see these structures everywhere in other galaxies? Yes, turns out. The spirals are actually segmented spirals. Look at this straight one. There's another straight there, up there. Look at that very long structure, and then that one, that one. Turns out spiral structures, spiral arms are actually segments put together. And I think this is what we're looking at the Radcliffe wave. It's perhaps the gas deposit of the local arm, which I think is more important than we used to think. And you know, the Perseus arm has all kinds of problems. But we didn't stop here regarding 3D dust mapping. This is now on parsec scale. This is an unbelievable map. This is from information theory people. They really know what they're doing. I don't understand how they get such a good map, but they do have a map of 400 parsecs cube around the sun. And you immediately can see, oh, that's the Radcliffe wave, that's a split. But now, at the 1 parsec resolution. All these maps are available, and you should definitely use them. They're not the only ones. This is from the group in Heidelberg, the Max Planck. You have Sarah Rezai and Jori Kanulainen, and this is a paper where they, using a different method, argue that, see, here's a Californian Orion that is mystery. They're about the same size, they have about the same mass, but this one is forming 10 times less stars than this one. And they think they've figured out why, is that this one is much more sheet-like, while this one is much more filament-like. And same thing with Dharmavadena, where they do the same kind of study, or a similar study on other regions. There's clearly some differences in terms of the maps. This is early work, early days on dust mapping at this resolution. This eventually will be telling you the same story, I think. So what is Gaia then showing you? Showing from kiloparsec scales. So you have the mother of the GMCs. GMCs are embedded like pearls on a string inside them. Here's another structure, the split. And if you zoom in now on this map, the 1 parsec resolution, you get, like, we're focusing on Perseus, and here's Perseus then from the Leica map. And this is the time where I'm going to show you Perseus in 3 dimensions. The thing that I never imagined possible when I started playing with Gaia data a couple of years ago. So this is not PPV, this is now PPP. Now we have then 3 positions. We can of course add the radial velocity, understand finally how is matter flowing. We tend to be very quick when Mark said, you know, there's the hub and obviously everything is converging. I'm not sure it's that obvious because there's a degeneracy. And this is now the time to go and try to figure out exactly where is the mass flowing. Of course, that's Perseus. You can do that for the entire 400 parsecs. And first lessons we're learning is that one of the questions that was in the field for a long time, are these things filaments or sheets? It turns out they're both. And these have important implications for magnetic field and molecular clouds. Another thing we're seeing is that, so you do have these distributions that I believe are made, like the Radcliffe wave are made by the galaxy, but inside them they are highly structured and they seem to be very windblown. So the role of feedback in destroying them, just like Mark was saying before, it is very important, and it shapes them dramatically. Now let me talk about what you can do with this amazing data. Here's Orion. There's 4,000 YSOs from surveys like Spitzer, from McGeeth and all, and from Chandra by Feigelson. We can take all of these sources, cross-correlate them with Gaia, and this is work from a PhD student in Vienna, and just take parcels of the cloud and then calculate averages. In fact, so here it is, the cloud. Now let's just take averages, groups of parcels of cloud, and just plot the sizes as a function of distance. And you suddenly realize that this is which nebula is really, halfway between us and Orion, although it somehow seems to feel some kind of flow because you have all these comet-like structures. And then you learn that this cloud turns out to be a very interesting, mysterious. It's a very narrow filament, but it's actually L-shaped. So the head of the cloud where the Orion Nebula is on the plane of the sky together with Orion B, but the tail flows back by hundreds of parsecs and reaches after, even 500 parsecs. Now, we do have these parcels, and already you're learning a lot about the 3D shape of the clouds, but we can take these stars that are attached still to the gas, these class 2s from the previous surveys from Spitzer, for example, and we have velocities for them. So together, if you take those velocities, the radial velocity, you have the positions, you have everything to figure out where they were 7 million years ago, and you can predict where they were in the future simply by knowing how to trace their orbits on the galactic potential. And this is what we did And what you find is this is 7 million years, and then to plus, minus to plus. And you see Orion used to be a much longer filament 7 million years ago, but then something happened. And that something, we believe, is an immense feedback process, or feedback event that took place about 6 million years ago that completely bent the head of the cloud. So you see the head of a cloud is now turning back and again moves faster than the tail of the cloud. The tail of the cloud doesn't even know yet about it, but this is where all the massive stars are in Orion. This is the Orion Nebula, the integral shaped filament is there. And then there's the small other clouds that are flying in all directions, and these are the tiny little cometary globules that we see. So something happened in Orion that is completely changing the dynamics and controlling the dynamics of the gas as you see today. So the role of feedback is clearly very important in this case in destroying the Orion array cloud. So we're talking about distance of 100 parsecs, and you can calculate rough numbers for the momentum from how much energy do you need, and if you just assume supernovae, which clearly is not the case, you need several supernovas, and we do have populations in front that will provide that. Now, if this was for Orion, and this is a work that started because now let me show you what we're seeing here. This is the sun is in the middle. Here's a view of the Radcliffe wave. Orion is here, and then Taurus, Perseus, and so on. On the other side, you have Scosan, and you have Chameleon, Musca, Corona, Lupus, Ophiuchus. And in the middle, and we got into this because we were very puzzled by the motion of Taurus. Taurus, we thought, is being affected by a shell discovered by Shmuel Bialy, the Pertau shell, and it should be moving out with the shell, and it's not, and it should be. And then we realized that, well, there's another bubble next to the Pertau shell. And this goes to the point you made before. There's bubbles everywhere, and we think that what's happening is there's pressure coming from the local bubble that's perturbing Taurus. Taurus is a kind of sandwich between two bubbles. Now, what we could try to do is what we just did in Orion, and we know the population that powered the local bubble. This is the Scosan association. Let's do the same thing. Let's go back in time. Again, we know the positions. We can assume that, in this case, the entire bubble is supernova-driven, neglect radiation pressure and winds, and fit time of explosion, ambient ISM, and we get something like this. So somewhere 70 million years ago, Scosan starts forming. In particular, older clusters turn out to be the most massive ones, and the first supernova started exploding. This is the sun. We were just passing by. We are still just passing by. As time passes, the bubble expands. As the bubble reaches gas that it was now Taurus, you have star formation, and the same thing in gas that is in the split, and until you got to about today. So this is, again, the Leica map in dust, Radcliffe wave split. The tracebacks point to a common origin to all the clusters in its Scosan, and we cannot but think of the model of Inutsuka and collaborators, where you do have this bubble-dominated formation of molecular clouds. This is probably not the case here 100%, but it's clearly, so if you take all the mass that was evacuated by this bubble, you get the mass of the molecular clouds. The molecular clouds are on the surface of this bubble. And it's not probably just this the case, because there was gas there. There was the Radcliffe wave and the split. But surely this contributed to enhance star formation in the surrounding of the sun. So you cannot do, again, a momentum analysis. We would need 15 supernovas to explain this bubble. And if you do, this was known before from population synthesis, you need about, the population produced about 14 to 20 supernovae. Now, one interesting question that we get asked all the time, why is this bubble why is the sun in the middle of the bubble? And well, it is now, it wasn't. The sun was 300 parsecs away, and about 6 million years old, the sun entered the bubble. Thanks. And this is where the sun is now. So why is the sun in the middle of the bubble? I think the answer is because there's bubbles everywhere. It's probably, as you've seen the image of NGC 628, it's probably hard for the sun to be outside of a bubble than inside of a bubble. These statistics are still needed. Now another question is, what does it mean for Earth? And this is very, very interesting because the timeline for the sun entering the local bubble is consistent with the supernova iron 60 supernova iron deposits on the Earth's crust. This is work by physicists at the University of Vienna. And where they find that from this analysis of these deposits, there's a peak about 2 million years old. This is studied as a supernova from, this is 2 million years old. This is when the sun was very close to SCOSAN, in particular LCC. And the idea is that the supernova exploded 2 million years ago that enriched Earth. And then there's a new peak. The peak was all there, but we have a new explanation. This is probably why when this peak is when the Earth enters the local bubble, the heliosphere gets crushed, and we get exposed to the ISM. And I have to, this is a very interesting topic, but this is more for the rest of the end of the week. I want to end on the young stars, and this is something that Gaia was designed to do, is point sources. And I have to start with the work from Kerr and collaborators. This is a PhD thesis where they take an approach to take the entire, in this case, 333 parsecs from the sun and do a complete, as complete as possible map of the young stars. One thing they did not notice on their map is that this distribution, now you're probably familiar with, this is the Radcliffe wave, and this is the split. Not much in between or out there. Okay, so they do find 37 groups. This is work in progress. They then have several papers now on particular regions. And I think this is going to tell us a lot about, we learned from Spitzer from 0 to a few. This is now from a few to 50, 100 million years. And it takes us to how do stars leave home? How does the galactic field get formed? They're still telling, they're very young still, they're still telling you about, they still have the memory of where the gas is. So they're still somehow connected to their distribution. And this is now what you can do, and this is very, very recent work, it's an AstroPH, when you not only take, this is typically, we've been using HTB scan a lot in the community, when you take, you spend some time and try to tailor your tools to the problem. And this is done, in this case, where this is SCOSAN, but SCOSAN now broken into 34 groups that we can tell they're different. So this is then in 5D, and this is, these are clusters. And by the way, if there's one thing you have to learn from this meeting is that all stars form in clusters, Mark. And here's the explanation. None of these clusters is bound, and I think what the problem is, you should always say is bound after cluster. All of them, and look how fast this is aged. In 20 million years, look how the young ones are all little. This is volume, by the way, not number. But as they age, they expand. They're always expanding very, very fast. But in fact, we have a hard time finding stars that are not inside a cluster. And by cluster, I mean an overdensity over the background, which is the definition we should be using, because no one can measure boundedness. When you do that, you have this new view on the star-forming regions, and in a sense, they're much more complex than we would love to. And an obvious thing is this guy, just this for more the end of the week. There's a region here called Upper SCO, where a lot of disks get aged. Look how many clusters are towards Upper SCO. There's clusters as old as 20 and as young as 5 in what we used to call Upper SCO. Okay, so be aware, if there's anything common in Skosan and to other regions, our disk ages have to be done much more carefully because we have to know where your star comes from. And typically, you might have an error in it. This gives you this type of data, high-resolution star formation history. Look, this is how the core was formed. This is where most stars and supernovae were formed. These are the big clusters. And then the rest is peanuts. But it's interesting peanuts and tells you about the feedback. You form this cluster, these chains of clusters, the very young at the tip and then a gradient up. This is exactly what you expect from feedback. You have some sort of gas that's reacting to a flow regarding supernova or winds, and gets pushed and forms stars and causes this octopus kind of model where you have the main event and then this feet spreading out from the center. Now, young stellar structures, one thing that we start finding, and this is the entire community, there's a lot of people finding these structures, these very long elongated structures. This is 120 degrees on the sky. This is the southern hemisphere. And if you look at it on the Cartesian, you see that it's 400 parsecs long at least. And it's like a cigar shaped if you look it from the side. And this is what we have to get used to. This is what Skosan probably looks like. This has the mass, probably looks like in a 100 million years. This cluster has the mass of the Pleiades, the age of the Pleiades, but it looks like the Pleiades spread on a thin layer of breath. This is what will happen to Skosan probably in 100 million years, and this is the view from above, and the view along, and the view from the side. And if it's very sensitive to initial conditions, and here's your elongation of the structure, by 100-something million years, you have these very long structures that will continue. If you had a compact cluster, a bound cluster, then you start seeing tails forming, the typical S-shaped tails forming. Not if you have an association like Skosan or like this one. This is very important because the age, as an object, the age is 100 million years. If you're studying planet formation, you know a lot about 1 to 10. You have very few points to start studying. You have the Pleiades, but the Pleiades does not have a lot of planets. Turns out there's these papers that are finding planets in this object. And what about the rest of them? That was, we didn't know about those. What about the ones we knew, about the open clusters around the sun? They all have these long structures. And you need to use careful tools. You need to know what you're doing. But of 10 clusters from 30 to 300 million years, only one does not show these elongations, this corona, and that's a Pleiades. All the other ones show these very long structures. Probably the galaxy, but you have to keep in mind, some of them are so young, like IC2602, that you must probably have some primordial distribution. Here's an optical, how this is looking in the sky. This is 2615 at 2 degrees, 10 degrees, 60 degrees, the little tiny thing there. And this is what we normally call the cluster. And this is the cluster if you extract. You're very sensitive to low surface densities, and you find that even on a 10-degree box, you will be missing stars. You have to go for 60-degree boxes to see the entire distribution. Most of the stars are not even in the core, so we're leaving a lot of questions about what is the IMF of these stars, of these clusters. This is all new ground. Finally, putting it all together, very quickly, this is the new reality. There's a very long structure called the Ratcliffe wave, where all the GMCs are, together with the split, the ones around the sun. There's these spurs. Forget about galactic structure. Forget about Sagittarius arm. We have no clue at the moment what is the structure of the Milky Way. It's definitely not a grand design. It's definitely not a flocculant, but anything in between. Here's the zoom-in version. This is the stellar populations from Kerr. The stellar populations are tracking naturally the gas. And I'm going to end up with, remember this? This is how we started, and this is a movie where we fly through the Radcliffe wave, and the local bubble. Unfortunately, it's very dark, but here's your molecular clouds on the surface. This is Taurus, this is Cosan or Fucus, and as you get closer, we're going to get to the sun. You're going to enter the bubble. About now, you can feel the pressure. Now it's high pressure, and we're going to try to find the sun somewhere in here, and there it is. And then you'll see that it comes with its own heliosphere, and there's the Voyager just out of the heliosphere. This is probably what got crushed as we enter the local bubble and allow us to detect iron-60. And this is then what Gaia is giving you, is this fundamental context that puts together both the molecular clouds, the stars, and this is us going away, and in the local neighborhood. Are we living in a particular strange place? No, we're not. This is the galaxy that we know about. That is exactly the size of the local bubble, 200 parsecs there. So I think we're entering now with JWST, with ALMA, and now with Gaia, this new paradigm. Finally, we can go to one of these conferences, star formation near and far, and then we don't have the galactic people from Monday to Wednesday, and then they disappear, and then the extragalactic people arrive on Wednesday and stay until Friday. I think finally we getting out of that, because we're now starting to talk the same scale. We can do 6D, of course, only on a local kiloparsec, but we don't have statistics, we have one. And the extragalactic, this is work by the next speaker, by the way, will have the statistics. So I will stop here. Thank you for your time.
Thank you. Now you're welcome to question time of the 3D astronomy. So I cannot, yes, go ahead.
Hello, so thanks for the talk, and my question is about that. So all your 3D cloud structures are derived from dust extinction data, which may be not sensitive to high density regions. But now we also have Herschel, like Gold Belt survey data, which use dust emission data, which has a better sensitivity to the dense regions. So is it possible to combine these two kind of data together to make your 3D cloud like more accurate?
Very good question. So yes, you're absolutely right. So this maps all saturate at about 1-2 magnitudes of extinction, just where it gets interesting for star formation. But they still confine a volume. And we know that the Herschel filament will go, for example, that you can see with Herschel, you can see inside these halos. So we do see these halos, and we do see that there's a core, and the core information is not there. There is a way to combine it, yes. I mean, you talk to your friends that do signal processing, and they will, I mean, this is something that we're not doing, but someone will do this hopefully very soon. It should be, there should be no problem. No problem is exaggeration. The problem with these maps is actually computational. They're very computationally intensive, but they should be possible. And then we'll have, from sub-parsec resolution to 100 parsec resolution in 3D. That's a great question, but we don't have that yet.
Okay, thank you.
Question from the back.
Yes, thank you very much for this very interesting talk. I'd be interested in one of your ideas as to why Radcliffe wave is a wave.
Everything, so if there's something that Gaia is showing us, is that everything is oscillating. And it could be just the passage of the Sagittarius dwarf. This is like a popular explanation. There's many other ideas. For a long time, because it's an attenuated sinusoidal, we thought there could be some kind of gas that entered the Milky Way, so from the halo, and at some angle, and then it basically goes back and attenuates because it's gas. We don't think that's now very will be very exciting because we probably totally different metallicity gas. And this is something that I think we will probably see more and more, since now it's not a random distribution of clouds. You have these families of clouds. They're very well defined. We might try to see differences, metallicities between them, and maybe that tells us something about the gas where it comes from. The explanation, the one that works for now, but we don't know for sure, is everything is oscillating in the galaxy. It'd be very strange if it's not. But then you ask, where are the other redshift waves? And I think there are out there. We just need to know to look at them.
Masato?
Thank you very much for your talk. I have two questions. So
Sure.
The first one is that you mentioned that those star-forming regions have like combination of sheet and filaments. And could you comment on their geometry compared with the bubbles that you mentioned finally?
They feel the bubbles. Show me a couple.
All right. For example, the sheet orientation against the bubble. For example, that's my comment. Yeah, that's my question.
Orion Lambda. Orion Lambda is this beautiful ring. Now, of course, is in projection. But there's a cluster right in the middle. And, I've always imagined it as a more spherical distribution, but it's a beautiful ring. So if anything you learn from this is that at this scale, the clouds feel very much where is the source of feedback. They react to them, they form hat-tail structures. I believe Ophiuchus is just that. It's just, and like some of the hat-tail structures, this is just gas reacting to a flow in a very aerodynamical way. You don't even need to evoke more than that to reproduce a lot of these gas distributions that you see at these scales, at the parsec scale.
Okay.
Sorry, I have a second question. So that you mentioned that in total that would be like a 15 supernovae in terms of the
local bubble.
I mean, I think in terms of the total kinematics.
Yeah.
Then can you comment on how they happen distinctively in time? Is there any clue for that?
No. So I think the model uses. They don't explode at the same time. They explode, from -17 to now, basically, periodically. I can't remember exactly how this was done, but we don't have a very good, star formation history on the explosions of the supernovae.
Okay, thank you very much.
Question from the back.
Thank you.
Let's be quick. Question to be, and the answer to be very quick.
Okay, very quick question. Are there any correlations between the GMC properties and whether they might look like sheets or filaments? Or their location?
Yes. If you have, some of them will have a head. We have a part, so some of them you don't really, there's really no head in the sense that there's a part that has denser gas than others. And this is, you tend to see that dense gas is always somehow closer or facing a potential source of feedback, like your work.
Yeah.
Okay, next. Yes, please.
Oh, hi there. Thank you for the talk. The question is, we see that Gaia parallax measurements have been suffering from large uncertainties, especially in the more embedded regions, even in the solar neighborhood. So I wonder typically how accurate are the parallax measurements in these molecular clouds, and if there are any large uncertainties, how do you deal with them to extract any meaningful
So
results?
that's the reason why we went for not the fancy 3D map, but for just a single line of sight, the simple measurement possible, which is you just take all the stars and plot as a function of distance their extinction, and then you see this bump. So if you do this with Gaia data, you get about 5% uncertainties. 5% uncertainties gives you at this distance is the size of the width of a molecular cloud. So we're not just, we're just seeing the first surface, and then there's a big mistake we're making because the cloud extends. No, it doesn't. I mean, the clouds are relatively narrow. So yeah, 5% if you use Gaia data alone.
Question from the back.
Right. So you mentioned that spiral arms are collections of straight segments. I was wondering, in your opinion, what we would learn from that? What is the significance? What you would think would be the significance of that?
Well, for me, it was like a big relief because the Radcliffe wave was very, very narrow to the point of people saying, "You made a mistake. There's no such thing as so narrow, so long." I don't know about the. I mean, the papers by Dongya. Simulations of spiral arm formation, it has to go into this transient, long-lived discussion, Lin and Shu versus the more modern view where things just pop up, like the wave, the crest of the wave pops up, like in Marx, and then disappears, instead of a crest of a wave going around the galaxy. This is all in that realm, and I'm definitely not an expert on that to comment.
Next one, yes, from the back.
Thank you, Joao, for the great overview. I had a question about the elongations of the clusters that you show in X, Y, Z plane. If you look at those plots, you can see the elongations in the X and Y plane and not in the Z plane. Is that because of the galactic dynamic, or do you think it's still observational biases due to unknown biases in parallax estimates? Because X and Y only appear where we actually measure.
I think this is what you expect, and this is what I think I needed to learn a lot, is what it means to live in the galaxy. There's a this potential, and this is that movie I showed you. Regardless how you start, you do have some initial distribution, but you end up always with this very thin, butter on the toast kind of distribution. So this is what happens. This is why there's no, the way I would answer is, I don't think there's any uncertainties. This is what you expect if you take, these, by the way, these have n-body calculations in them, but they make no difference because they're low density. So no matter how you start, you're going to end up always on these very, very, very long, narrow structures. And this is something that I've been learning about living in a galaxy.
Okay, from the back, yes.
Okay. Thank you very much for the great work. My question is this, that did you make a comparison between the PPP structure and the position velocity structure of the cloud?
That's a great question. This has to be done. There's one paper, though. There's at least one paper, no, more than one now. There's one by the French. Sorry, I'm blanking out. I'm jet lagged.
Okay, thank you.
There is two papers. If you send me an email, I'll send you these two papers. It's just the beginning. It is a wonderful avenue. So suddenly you have not only the 3D, the true 3D of the structure, you have the velocity. So you can understand what is velocity gradient along these filaments. Does it really mean that matter is flowing, or the opposite, matter is outgoing? That I would argue it's most likely to be feedback driving stuff away from these clumps than stuff accreting on these clumps. Okay, but this is to be done. This is just a door that's now open for investigation.
Last question from Vlad.
Thank you, Jean. Excellent talk. So this is a question actually both to you and Mark. I think I missed the point in Mark's argument as to why not all stars should be formed in clusters. So I was actually very happy when you said that that's not the case.
Yes.
So, if you could.
Sure. So Mark is wrong, I'm right. Here. When you start doing this type of work at this sensitivity, so you're sensitive to 0.5 kilometers per second and 0.01 sources per parsec, you start dividing what we used to call, that's the dispersed population. We don't find a dispersed population. Everything comes in a cluster, in the sense that a cluster being an enhancement over a background. What Mark was saying is, he's talking about, when he talks about cluster, he talks about the bounded cluster. But all these clusters were bound when they were formed. They form the clump, in the molecular clump. So this is why it's very hard to use boundness when you're talking about clusters. I prefer to call them clusters in a mathematical sense of the word. They're just an enhancement over a background. These are bound for a very tiny time, and then they immediately disperse. You can have ones that can make it to 100 million years, but then they disperse. So I think this is just, a lot of it is semantics, and a lot of it is because he's wrong and I'm right.
Okay, so it's nice, it's a good time. So let's thank our speaker again.